Thanks for coming. So I'll just briefly start. Show of hands, who here doesn't use Runhouse? Okay, all right, great. So about half the room, I guess. That kind of backfired on me. So who we are, we generally hold the hypothesis that we're still in the sort of Hadoop era of machine learning infrastructure. So, you know, if you're doing things like single node or without a tremendous amount of repeated execution, then you can kind of sustain it. But if you are doing things on a distributed basis or with a lot of recurring training or repeated execution, you often need to divert some of your machine learning engineering resources or even staff up a team to support that. We just believe that a lot of this can actually just be directly automated through the interface with the compute itself. So Runhouse makes distributed machine learning field serverless. It seamlessly dispatches and distributes your machine learning workloads in code. It's unopinionated about the choice of distribution that you choose to use, and it executes those workloads inside of your own infrastructure. And it just saves you a lot of time managing your own ML infrastructure, doing ML ops, building templates, adapting templates, dealing with kind of copied and pasted code, things like that. We're New York-based. We're open source and AI systems experts. So I want to just share kind of our starting point for the design of Runhouse, and it's actually kind of critically intertwined with Ray. We ourselves are Ray users. We've been using it for a long time. Actually, like the first thing that we did after starting Runhouse is this is just coincidental timing, was we came to the Ray Summit in 2022. And there, you know, we saw this amazing vision of essentially solving distributed compute with like a unified DSL. And Ray does that extremely well. Inside of a cluster, Ray is extremely portable, and it provides a sort of containerized distributed setup that allows you to define your distributed work and then layer it onto different clusters that you know, essentially that you can, you know, dynamically bring up and down, and the same code will work on different clusters. Most of this is facilitated by serializing Python, which has certain advantages and disadvantages that I'm sure everybody in this room have run into at various times. So by dispatching work throughout the cluster, you get the full expressivity of Python. You don't have some sort of narrow IR like Spark, for example, that restricts the activities that you can do inside a distributed system. You have portability across operating systems and hardware, just Python's own portability, and you get statefulness. This is like one of the biggest wins that the Ray team introduced by introducing such aggressive reliance on serialization is actors and spilling over and being able to distribute work across the cluster wherever the resources are available. But this came with certain trade-offs. So there are certain pros to this approach. One is that the same code can reliably work on any other Ray cluster with the same dependencies. So this is that sort of containerized distributed benefit. Portability within a cluster, you can take the same block of work and just schedule it wherever the resources are available. The serialization facilitates that. And then fault tolerance, laziness, optimization, these are all things that Ray relies on GCS and serialization to facilitate. But there are certain cons. So one is that the cluster is highly coupled together. And if you lose a node, generally you're losing the cluster. And even removing nodes just to kind of like dynamically manage your resources is not something that is straightforward to do, or many people do at all. Probably the most significant trade-off is the version consistency requirements. So you have to very tightly maintain consistency in the Python, Ray, and library versions throughout the cluster, and anybody who's using it from the outside, essentially, if you're connected as a client. And then lastly, nodes, notably client nodes, should not be in multiple clusters at once. And so these cons actually introduce a few complications when you're looking at the outside of the cluster. So inside of the cluster, this is all super consistent and super fault tolerant. But the workflows that involve outside cluster activities are challenging. So for one, having collaboration is something that people run into quickly when they're trying to use like long-lived Ray clusters. You have multiple people who are connected to the cluster as a client. All their minor versions have to exactly match, and that actually generally doesn't work. People end up not really connecting through the client. They end up basically just like interacting with the cluster primarily via running scripts, which has its own automation downsides. It like cleaves your program in half, and it makes it so that you can catch errors less dependably outside of the cluster. And then another major shortcoming of this extra cluster or a complication is orchestration between clusters. So if you have one client, it can't really connect to multiple array clusters at once. And so if you wanted to do one portion of your work on like a cluster on GCP or within GCP and another portion of your work inside of CoreWeave or pick another cloud, pick another region, that workflow also doesn't work when you're working through the client. You'll have to basically dispatch those as one-off scripts. And then lastly, sharing resources between clusters is kind of fundamentally blocked. So if you had, let's say, a batch evaluation job that multiple different pipelines or workloads relied on, you probably just want to take that group of 4 or 8 GPUs and have everybody call into the same GPUs, but you can't really share actors in that way. You have to essentially replicate those resources everywhere you want to use them. So we built Runhouse to solve these extra cluster problems, and we refer to it as a sort of distributed, a serverless distributed ML system, and we solve these problems of extra cluster dispatch or orchestration. So for one of the most important decisions we make is that there's no local runtime. So don't think of Runhouse as like another layer of Ray that's operating outside of the cluster. We've built it so it operates purely inside of Python itself, so that there is no runtime to fail. There's nothing that can fail locally other than just like the Python interpreter itself. If a cluster goes down or fails or a job fails or ooms or whatever, you have extremely dependable fault tolerance inside of the driver program to catch that error and then just bring up a new cluster or reinitiate or whatever you need to do. And in practice, we've seen that our users have fault rates in their trainings have completely plummeted because they have this level of control, especially as compared to just executing kind of arbitrary remote scripts where you have very little visibility or ability to systematically catch those errors. So there's no local runtime. That also means you get the full expressivity of Python as a language in the way that you build your workflows. So you don't have sort of narrow DAG DSL like Airflow or Argo dictating what exactly you can do in the control flow of your program. You just get arbitrary Python. And you can also just develop and run it anywhere. So we don't even have a sort of magic CLI incantation to launch the Python, which is very common. You can run Runhouse. You can dispatch code to your server, to your remote clusters in any IDE, a notebook, a fast API app, Airflow, it doesn't matter. Anywhere that Python runs, you can use essentially full-scale machine learning compute inside of that, like, narrow Python interpreter. We support arbitrary compute, so we orchestrate across any cloud, any region, instance type, or even distribution type. So you could say, I want to distribute this Ray, or you could also tell us, I want to distribute this PyTorch distributed code directly, and we'll create your replicas. And then there's also node code serialization or coupling. So the calls to the clusters are actually over HTTP. And so that means that they're very loosely coupled. The system is extremely fault tolerant. And you can bring up and down the clusters on demand as needed, which just allows much greater resource efficiency than if these resources were all coupled together in a single cluster. The way that it looks, this is not a coincidence. I was on the PyTorch team before starting to work on Runhouse. It looks like PyTorch. You could think of it as sort of like an eager mode orchestrator. You tell us what compute you want, and then you tell us what Python code you want to send to that compute, and we send it over. And then you basically get back a callable or a stub, which looks identical to your original class in the cases of classes. We support statefulness the same way that Ray does. We're using Ray under the hood, and we support Ray on a first-class basis, but you'll notice there are a lot of similar concepts. And then that callable will just basically call your code over RPC, and you can use this for anything. So serverless distributed is very carefully chosen language because most serverless systems that you'll see are auto-scaling. They're built for inference, and that model of auto-scaling really depends on single node containerization. Those systems don't work well for distributed workloads like training or batch evaluation. And so we think this is basically the first system that introduces this like serverless distributed in Python model where you're not basically just sort of dispatching off scripts and you get lots of the development ergonomics and control benefits with that. Another important question you might have looking at this code is, why no decorators? Everybody uses decorators, and this is also a very intentional decision. When you're writing Ray code, you're really writing a distributed DSL for your program itself is a distributed DSL. And so the decision to use Ray and the choice of the specific resources are actually tied to the code proper. When you're using Runhouse, actually, we don't want to affect your underlying code, right? Your training loop that you're dispatching with Runhouse is your training loop. It's regular arbitrary Python, and we want to allow you to reuse it as many different ways as you might want. And it's actually extremely common to have one training function or training loop, and then run it on a single process for certain types of testing, and run it on multi-process for one job, and then multi-node for another job, and then many nodes and many processes for HPO. And we don't want to be opinionated about that. We want to make it so that you can make your code as modular and reusable as possible. Another important detail about our choice not to use decorators is actually that we support much more of the existing Python ecosystem out of the box. So we've heard users who are using Flight or Prefect, their decorators will get in the way of being able to use systems like MyPy or PyTest. And we just don't want to get in the way at all. We just want to dispatch your work to your clusters as you ask us to, and leave your code alone for pretty much everything else. And that's kind of a broader theme. We also leave your IDE alone. We also leave your infrastructure alone. We're kind of just very strictly following instructions to distribute your workload. So 2 years ago at the Ray Summit, the Ray team brought out all the star power. OpenAI, Instacart, Shopify, Spotify, and Uber all adopting Ray, and following this particular model that really progressed the ML development workflow relative to the notebooks plus Airflow standard at that time. And it was based on a few things. One is moving workflows fully in Python, both from the perspective of having much better code collaboration, DevOps, and rigor in the way that the experiments are actually run. But also from the perspective of fault tolerance and overall just resource efficiency. So this is compared to breaking up your pipeline into multiple, into an Airflow DAG, and having that whole research to production and kind of execution bottleneck. The next major choice of all these, factor in the way that a lot of these people adopted Ray was using ephemeral clusters. So just constantly launching ephemeral clusters all over the place. When researchers arrive in the morning, they get a Ray cluster, they do their development directly on the Ray cluster. When they push to production, their Airflow pipelines or their their serving is all on Ray clusters, and they just kind of have to launch one-off Ray clusters all over the place. That's why that's kind of the analogy to containers that I was mentioning earlier. And the code being identical across research and production was one of the main things that unlocked. So let's talk about how you can use Runhouse with Ray to progress that model further. Solving the, Runhouse with solving the extra cluster problems, and Ray solving the intra-cluster problems. So the first way to, this is probably not readable. We kind of described 3 different steps of how you can adopt Runhouse with Ray to improve your ML development broadly. The first is to dispatch Ray with Runhouse. The second is to modularize your workflows and even potentially make them multi-cluster or multi-cloud. And the third is to reuse clusters and services across users and pipelines. So getting into more detail, this is what dispatching Ray with Runhouse looks like. So I have a Ray tune job here. And at the bottom, you'll see the Runhouse code. Basically, all I'm doing here is just specifying the cluster that I want to send this job to, and then wrapping my Ray tune code in a Runhouse function, dispatching it to the cluster, and then calling it. This could have been a class. There are much more creative things I can do to dispatch it, but this is pretty much the simplest way to actually develop and deploy a hyperparameter optimization job without having to disrupt anything else about your dev workflow. I can run this from a regular IDE. I don't have to be SSH'd into a Ray cluster. I can develop this from inside of a local Jupyter notebook. I can push it into Argo without changing anything about how my Argo pipelines launch. I can push it into a fast API app. It'll run anywhere, and it's a full-fledged Ray HPO job. And so this is why we think dispatching Ray with Runhouse is a really powerful paradigm, because you also have all the iteration benefits of running this over SSH, and that's kind of the magic of Runhouse. The magic is basically that we have about a 1-second iteration loop, which feels the same as running this code over and over again in a notebook. And then speaking of notebooks, same thing. You can, inside of a notebook, take your HPO job, dispatch it, and there are a few notable benefits here that you might not necessarily think of. One is that your notebook cells don't lock up, because actually the objects and the interpreter that your HPO job is running in are on the cluster. They're not in the local notebook. And so you can run these things async. You don't have to lock up your notebook when you run a cell and wait for it to finish and have no access to that object. You can actually get at your objects from multiple places, which is pretty cool. That's not a thing that I was really expecting out of the system. And then when we started using notebooks with the system, it's like amazing. You can dispatch and trigger a training on your remote cluster, and then you can SSH onto the cluster and like do a bunch of like much more detailed introspection of what's going on with the training. And then you can even in the notebook in a different cell call an eval job on the training class that's currently in flight to ask it like, what's going on, how is this progressing? So the parallelism from multiple different places is nice. As I mentioned, you can SSH in, you can disconnect and reconnect because the core execution is happening on your cluster. And then another major advantage is that you can work with your local repo code. Right, so the code that's in my team's shared GitHub repo, my training function, stays inside of that, in that repo locally, and it just dispatches through the notebook. I don't like copy it into some hosted notebook IDE or something like that. And then maybe most notably, I can share this notebook and cluster with a colleague, and they can just run cells, and they'll be running on the exact same cluster, and that's a level of collaboration that most people don't get with like a hosted notebook system. Other things, other advantages are just much better debuggability. So as I mentioned, you can kind of approach your workflow from multiple different perspectives. We built this with debuggability in mind. That's also part of the reason why it's modeled after PyTorch, is it's all eager. You can step through your code. As I mentioned, you can just share clusters with other people, and they can access them natively. And by not having these sort of serialization, dispatch, other people can actually dispatch work at the cluster, and it'll just work even if the minor versions don't match. As I mentioned also, scheduling something in production is trivial. You can see there's Argo code on the left there that just runs the script. And because the script has mixed execution, right, it's running a normal Python script, but now it's actually launching my like potentially 1,000 node training job on my cluster inside of that Python script. I don't have to adapt Argo to be like able to launch array clusters, for example. And then also, as I mentioned, fault tolerance is significantly better. There's no cascading failure. There's no local runtime failure, right? Like it's just a Python interpreter locally, so there's kind of nothing that can get broken other than like Python itself. And then there's no like restricted DSL, like an Airflow or like another sort of DAG subset of what you can do. So actually, I've shown some example code here, which is strictly illustrative. But we have users that will launch a bunch of training pipelines at the smallest possible scale, and then they know that like a third of them are going to but it depends on the data that day. And the third of them that they just catch the tear down the cluster, just bring up another cluster. That's all in their actual pipeline code in Python. That's a level of control flow you can't do with like an orchestrator, right? Only in Python itself. And that also kind of speaks to why you get such good fault tolerance, because if you're struggling with a particular error that's showing up in production, all you have to do with Runhouse, because it's all Pythonic, is catch the error. If you were doing this through a script-style dispatch, you're talking about like parsing logs to figure out why this thing failed, and it's significantly more challenging. So the next major benefit is modularizing workflows, or the next way to integrate these together is to modularize your workflows. So you could think of like dispatching Ray with Runhouse in the terms of like that Uber example where it's like a really wide training script and you're just dispatching the whole Ray program up. But you can also break it up to significantly modularize your system and give yourself a lot more control. So this is to have better resource efficiency, be less monolithic code, not have as much kind of configuration up front in the way that your remote code is launching, and also to be less brittle. But each service or each deployment in Runhouse is completely separate from one another. And so in principle, these different sections of the pipeline can just run on separate clusters also. This is kind of the first pattern that we've seen, pipelining these executions so that you can be really resource efficient. So only keeping a cluster up while you're actually using it. In that Uber example, you're actually keeping the whole cluster and all the resources up throughout the pipeline. But if you break these things up and you just dispatch them separately with Runhouse, you can tear down the clusters you're not using. So just use like some CPUs for the pre-processing, tear it down, use some GPUs for the training, tear it down, or be clever about how you use the resources. And then also, because each of these clusters are completely decoupled from the core runtime, you can have multi-cloud, multi-region. It's totally arbitrary. We had users who just like told us one day, oh, our trainings were all running on AWS, and then yesterday we moved them all to GCP because we got a bunch of credits from GCP. And they're their control plane was still in AWS. Argo was the thing that was actually triggering the job. It was less than a one-day activity for them to basically go multi-cloud, which is something a lot of enterprises struggle with, for years. Avoiding config explosion is a really subtle but important problem. Like, if you only launch your remote jobs as like scripts, you end up with these massive growing configs that kind of have a jagged or have a sparse. There's a lot of like tribal wisdom which combinations of configs actually work with each other. Whereas if you modularize your code, the config is captured in code. And then finally, like really flexible distribution and scaling. You can use arbitrary distributed systems with your Runhouse clusters. So you can be, sending Ray code with one step and Spark code with another step and PyTorch distributed in another step. Truly doesn't matter to us. And you can scale these things completely separately from each other. Final thing I'll mention is reusing clusters and services. We found that people save a ton of money reusing clusters across multiple stages of their pipeline, avoiding reloading data multiple times, or just to more cleverly shrink and grow the clusters depending on the structure of the pipeline. And reusing services is kind of the point I mentioned earlier. You might have 10 researchers and 10 pipelines that are all calling the same BERT evaluation step, and they're all allocating 4 or 8 GPUs separately. Runhouse makes it trivial to basically turn that into a service and just have many different clusters or pipelines calling it. So I'll just briefly go over a case study. We had a team that came to us. They were using Airflow and SageMaker. They were running hundreds of trainings per week. And they couldn't onboard new customers because 50% of the team's time was spent on infra. Notably, their training failure rate was around 40%. After they migrated to Runhouse, they saved 50% on their compute costs immediately through combination of easy-to-implement techniques that just required a little bit of insight and better control of the underlying hardware that we provide. And then their job failure rate dropped to less than 1%. And the biggest impact was their dev velocity. They moved their evals and HPO to Runhouse, and then this was actually the team that migrated to GCP in about a day. And now Matt's going to talk about our UI management and observability.
Thanks. Yeah, so as Donny has shown you, Runhouse is a pretty powerful tool for creating collaborative ML pipelines. The API fits into your existing workflows and empowers engineers to focus on machine learning, not DevOps. And on top of that, we have a UI that offers management and observability layer, much like a modern control panel for your ML. I'll walk you through some of the core features. By logging in with a Runhouse account, you can save clusters, functions, modules, and any associated resources. These objects store necessary information to identify, fetch, or recreate the ML artifacts. This slide shows our main dashboard view where any primitives you save will immediately appear. You can search by resource name, filter by type, and explore resources that are shared by others. Some resource types, such as clusters, show additional information, such as the cloud provider or status, to add a little more value to this UI. As you've seen, a key primitive in Runhouse is cluster. Clusters are abstractions for hardware configurations, including static machines and on-demand clusters that launch on your own cloud. The Runhouse UI provides an overview of your clusters, where you can quickly check which are running, terminated, or experiencing an error. Especially for teams running on multiple clouds or regions, a simple list view can be a huge time saver. When you select a cluster, you'll see the screen behind me. Resource pages display metadata and general information about a saved cluster or resource. For clusters, this includes information about the config, like the cloud provider, instance type, IP address, ports, and even the pricing per hour. Resource pages even expose resource or history, metrics, logs, and access controls for collaboration. I'll dive more into that in a minute. You also saw how you can easily dispatch your functions and modules to clusters via the Runhouse API. So let's briefly see how these are represented in the UI. Deployed functions and modules store basic metadata as well as method, signatures, and information about the environment in which they are running. These connections allow you to easily navigate from a function or module to the associated cluster, assuming you have access. A small button on the top of the page even indicates whether that cluster is up or down. These features are meant to further improve your debugging workflows by connecting telemetry across the platform. As you likely know, observability is both necessary and complex for ML infrastructure. Memory errors are common, and knowing that you're effectively using your compute is crucial, especially considering the costs involved. Using your access token, the Runhouse daemon running on your clusters can send and store telemetry data. Our goal with this data is to answer important questions ranging from, do I have enough GPUs to run this training module, or just wondering if your cluster is running. You can answer these questions by stringing together various other services, but Runhouse combines metrics, logs, and traces all in one place. And we're able to collect this data where your processes are running, not at some arbitrary level. These screenshots show a couple of the interfaces we've added. For metrics, you can collect memory usage and utilization for both GPU and CPU on your clusters. And these charts break it down by EMs or workers and nodes, so you can discern which functions or modules are actually consuming more resources or causing problems. Logs are automatically persisted, and they're available in a simple UI or as downloadable files over a select time period. This allows you to gather quick insights and provides you with an option to dig deeper when debugging. Runhouse uses the OpenTelemetry protocol to collect and store this data, so even though we think that Runhouse can provide a uniquely helpful UI, you also have the ability to forward metrics, logs, and traces from our collector to your platform of choice, such as Grafana or Honeycomb. Lastly, but most importantly, or not most importantly, equally importantly, we'll talk about collaboration. Collaboration is built into the core of Runhouse, and that's why we often compare our product to Google Drive for ML. Along with the Python API, you can update and manage access to any resource directly in the UI. You can add your teammates to your resource just by specifying email address and access level. This is perfect for turning components of your pipeline into reusable services. For example, you could share a preprocessor running with on your company cloud with a colleague. This will allow them to use it in their own experiments simply by initiating it by its name in Python. Of course, they'll have access to everything else I've just shown you as well. We're currently testing organization accounts with our partners as well. These can facilitate even simpler sharing by saving a resource directly to an organization instead of a user. Then any member of that organization would be able to access the resource. The logic's similar to how things might work on GitHub, for example. Lastly, I'll add that these screenshots I've shared are not just mockups. This is actually a live platform, so you can try it yourself at run.house.
Yeah, so just in closing, drop us a star on GitHub, and please share feedback, or if you're interested in trying out the platform, let us know if you're interested in partnering with us on design, or just sharing one-off feedback. And then we talk to hundreds of companies about their machine learning infrastructure. There's a huge gap in the architectural standards for machine learning infrastructure today. We found that there's a lot of craving for even just discussion of best practices. If that's something that's appealing to you and you want us to just audit your stack, feel free to send us an email. And yeah, thank you. Yeah.
One thing I wonder in the code examples you showed. So let's say I have a very sophisticated or difficult script I want to run with very dependencies both locally and externally. How does this get dispatched to the cluster?
So this is a huge. Sorry. Oh, so the question is, if I have a complex script that has local and remote dependencies, how do these get dispatched to the cluster? This is actually an area that we've spent a lot of time automating. So we do this at multiple levels, and you want to vary these things depending on whether you're doing them in kind of like rapid experimentation mode or in production. So in rapid experimentation mode, we basically just make it extremely ergonomic to specify dependencies on the cluster, and those are somewhat free-form, right? You can pip install, you can sync over local code that's going to get synced and installed over. You can, if your code has a requirements.txt, we'll detect it and install the requirements.txt. All those things basically are just kind of improved ergonomics for rapid development. And then in production, you want to freeze that in some way, right? So either you specify a container. You can specify a container as a kind of base image in research as well, just to save yourself the installs or to start from something similar to production. But in production, you either want to fully freeze it and just specify your team container, and then we won't install anything, we won't sync anything over. That'll just be basically what's expected to be available in code on the on the cluster. Or you can specify a base container and then have, let's say, a certain set of programmatically installed dependencies on the cluster or things that are synced up. It's just as frozen as a container is in a way, except that downloading from PyPy or Conda is somewhat stateful, right? So you can think that your installs are totally identical one day to the next, but some new release could break them. But if you need that level of dependency isolation, or I forget what the term is, then you can also just fully package into a container. We support all the way through. Yeah. Okay, cool. Thanks, everyone.